Okay, guys, we've looked at the basics of probability. Now we want to look at conditional probability. So conditional probability is where one thing affects another. Generally, you can think of it like if I have a bag that has a number of different marbles in it, just say I got 3 red marbles and 4 green. If I take out a marble, just say I get a red marble, there's a 3 out of 7 chance of getting a red. If I don't put it back in, if I want to get a red marble then a green marble, if I don't replace it, I've now got 4 green marbles out of 6. So we can see this probability and this probability affect each other. So one event is dependent on the outcome of the previous event. Another way to look at it would be if I said I'm going to roll a dice, my sample space would be 1, 2, 3, 4, 5, 6. If I said A is the event of an even number, we get 2, 4, 6. And I said B was a square number, 1, 4. If I asked you what's the probability of A happening given that I know that B has happened? If B has happened, I got a 1 or a 4. The probability of A happening is 1 out of a possible 2. So the probability of A given B is a half. If B has happened, the probability of A also happening is 1 out of 2. If I said the probability of B given that A happened, if we know A has happened, the probability of B happening, well, that's 1 out of 3. However, if I just said, what's the probability of A? The probability of A is 3 out of 6, which is a half. And if I said, what's the probability of B? That's 2 out of 6, which is 1 out of 3. You can see these things are the same. So we would say these events are independent, which is what we're going to look at next. Because one thing doesn't affect the other. However, if we change B, instead of saying it is the square numbers, let's say it's the prime numbers. So 2, 3, and 5. So there, A happening didn't affect B and B happening didn't affect A. So these things weren't conditional on the previous event. Now if I said to you, what's the probability of A happening? Well, that's 3 out of 6. 3 out of 6, which is a half. What's the probability of A happening given that B has happened? So if B happens, I've got 3 possible outcomes, and A is one of them. So you can see here, this has changed the probability of A happening when B happens. So they are dependent because A changes probabilities when B happens. And then if I said, what's the probability of B? Well, we know that's 3 out of 6, which is a half. What's the probability of B given that A has happened? If A has happened, we got 3 outcomes. The probability of B also happening is 1. So in this case here, they're different. So these are also dependent. Whereas before, they were the same probabilities, which means one doesn't affect the other, which means that they're independent. Now, for this question here, we need to go back to question 6, which was in my last video. It says, for the information in example 6, given that Simone had her teeth cleaned on a particular visit to the dentist, what's the probability that she also needed a filling? So we know we want to find the probability that Simone had her teeth cleaned on a particular visit. What's the probability she also needed a filling? So the probability she needed a filling, given that she needed a clean, which is the probability she needed a filling and a clean, over the probability she needed a clean from our conditional probability law. So we roll back, a filling and a clean is 0.05 over the probability of a clean, which is 0.35. Now you can't leave a decimal over a decimal, but if we multiply the top and the bottom by 100, we get 5 over 35, which is 1 out of 7. Now if I said to you, what's the probability she needed a filling? If we look back, the probability she needed a filling is 0.1. But the probability she needed a filling, if she had her teeth cleaned, is 1/7. So this probability has increased when I know that she has a clean. So these things are dependent because one thing affects the next. If they didn't affect each other, we would say they were independent. But these things are dependent because my probability has changed. If it's independent, the probability of a filling given a clean would remain the same as the probability of a filling. But in this case, we can see they're two different values. So having a clean affects the outcome of having a filling. You're more likely, if you have to have your teeth clean, you're more likely to have a filling. Okay, this is another case of conditional probability. It says in a certain town, the probability that it rains on a Monday is 0.21. If it rains on Monday, then probably it rains on a Tuesday is 0.83. If it doesn't rain on Monday, then probably it rains on a Tuesday is 0.3. So we know here, in this case, we know that Monday has to happen first. So let's say Monday. It can rain or not rain. And then we've got Tuesday. After raining on a Monday, it could rain on a Tuesday or not rain. Or after not raining on a Monday, it could rain or not rain. The probability that it rains on a Monday is 0.21. So that's 0.21, which means that's 0.79 because they have to add up to 1. If it rains on a Monday, the probability it rains on a Tuesday is 0.83. So that's 0.83, which means that's 0.17. If it doesn't rain on Monday, the probability it rains on Tuesday is 0.3, which means the probability it doesn't rain is 0.7. So we've got 4 outcomes. We've got rain, 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 not rain, not rain, rain, not rain, not rain. Now these probabilities are dependent because the probability of an outcome, rain, changes here based on what happened the day before. So we call these dependent probabilities. What's the probability of both rain on Monday and Tuesday? So the probability of rain, rain. It's got a rain and rain. So it's 0.21 times 0.83. 0.21 times 0.83, 0.1743. The probability that it rains on a Tuesday. So it can rain here on a Tuesday, or it can rain here on a Tuesday. So we know, now notice I said or, it can. The probability of rain on a Tuesday, we can have rain, rain, or we can have not rain, rain. The probability of rain, rain is 0.21 times 0.83. The probability of not rain, rain, well that is, oops, I should have just multiplied. That's not rain, rain, 0.79 times 0.3. Now we've already done the first one, plus 0.79 times 0.3, which is 0.4113 in total. What's the probability that it rains on Monday, given that it rained on Tuesday? So the probability of rain Monday, given that it rains Tuesday. Now, generally with probability questions, when you come to the third part, you use the first two parts. Not always, but a lot of the time. Now, we know our given probability is that it rains where those two intersect. So it's got to rain, probability of rain both days. That's where they intersect, over the probability that it rains on Tuesday. The probability that it rains on both days is 0.1743. Over that it rains on a Tuesday is 0.4113. So it's that divided by that. So I'm going to say 0.4238. Now, generally in probability, they will actually say to 4 decimal places. These ones, it doesn't matter because they're exact. But this one, because it is more than 4 decimal places, I should have said it needs to be to 4 decimal places. So in this case here, the probability that it rains on Tuesday affects the probability that it rains on Monday. Well, the opposite way. We know whether it's more likely or not. We know here the probability of rain on Monday is 0.21, but if we know it rained on a Tuesday, the probability of rain on Monday is 0.4238. It's more likely that it had rained the day before. Okay. Here, Adrian, Regan, Michael are doing the dishes. Since Adrian's the oldest, she washes the dishes 40% of the time. Regan's the middle, 30% of the time. Michael's the youngest. He is 30% of the time. When Adrian washes the dishes, her chance of breaking one is 0.01. So not breaking one is 0.99. Regan's 0.02. So not breaking one is 0.98. And Michael's the dud of the family. He breaks one 3% of the time when he washes, and 97% of the time he doesn't break one. We know the probability of Adrian washing is 0.4, 0.3, 0.3. So we can have Adrian breaking, Adrian, I should put intersects, breaking, Adrian intersects, not breaking, Regan intersects breaking, Regan intersects not breaking, Michael intersects breaking, Michael intersects not breaking. Okay, what's the probability that at least one dish is broken? Well, we know we can have Adrian and breaking. can't even use my own words. Probability of Adrian and Broken plus the probability of Regan and breaking a dish plus the probability of Michael and breaking a dish. So we get 0.4 times 0.01 plus, because that's one outcome, we multiply them. Then we get 0.3 times 0.02, another outcome. Or lastly, Michael and breaking a dish, 0.3 times 0.03. 0.004 plus 0.006 plus 0.009. We're going to get 0.019. For those of you who don't know how to multiply decimals, you need to know. If you've got 0.04 times 0.021, effectively we multiply those two numbers, so we get 84. And then we go, okay, we've got 1, 2, 3, 4 numbers after the decimal plate. So we need to have 4 numbers after the decimal place, so that's 0.0084. So that's what I did here. 4 times 1 is 4, and I need 3 numbers after the decimal place. Okay, given that at least one dish is broken, well, we've got that from the previous question. What's the probability that Michael's washing? So the probability that Michael's washing and a broken dish, given that a dish is broken, is the probability that Michael's washing and a broken dish over the probability of a broken dish. Now, Michael's washing and a broken dish, we know is 0.3 times 0.03. The probability of a dish being broken, we've got that from the last question. So we know on top we get 0.009, and on the bottom we get 0.019. Multiply the top and the bottom by 1,000. We get 9/19. So that's the probability that Michael's washing and breaking a dish, given that a dish is broken. Sounds about right. There's nearly a 50% chance that he's washing if a dish is broken. You can see here, it should be about a half. It's not exactly a half because the chance of them washing is in a different ratio, but it's pretty close. Okay, as part of evaluation for a school canteen, all students in year 10, 11, 12 were asked to rate the canteen as poor, excellent, etc. What's the probability a student chosen at random from the senior secondary college is in year 12? So the number of students in year 12 is 80 out of a total of 400, which is a 1 on 5 chance. The probability that they're in year 12 and rated the canteen as excellent, my experiences with this, it wouldn't be that high. 35 out of 400, divide them both by 5, 7 out of 24. Is that right? Huh? That's dumb. 5's 20 times 4, 80. Is in year 12 given they rated the canteen as excellent. So 12 given excellent. So that's the probability of 12 and excellent over the probability of excellent. Probability of 12 and excellent is 35. The probability they rated it as excellent, there's 160 students who rated it as excellent. Divide them both by 5, we get 7 out of 32. And then the probability they rated it as excellent, given that they're in year 12, that's the probability of excellent and in year 12 over the probability that they're in year 12. Excellent and in year 12, well, we know that's still 35, but now we're choosing them out of the number of students in year 12, which is 80. Which is 7 out of 16. So you can see the different outcomes based on the group we're choosing. Here we're choosing all the students who are excellent. Here we're choosing all the students who are in year 12. Okay, so here's a question from a while ago that has to do with conditional probability. There's a daily flight from Paradise Island to Melbourne. The probability of the flight departing on time given the weather is fine is 0.8. So we've got the weather and then departure. Okay, in March, the probability of the weather being fine is 0.4. So I'll say here's fine, 0.4, which means it's not fine, is 0.6. The flight departs on time is 0.8 if it's fine, which means it's 0.2 of not departing on time. The probability of it departing on time given that the weather is on the island is not fine. It's 0.6, which means it's 0.4 if it's not on time. Find the probability, particularly in March, the flight from Paradise Island departs on time. So we can either say, so the probability of on time equals the probability of fine and on time, or, so plus, the probability of not fine and on time. Fine and on time is 0.4 times 0.8. Not fine and on time is 0.6 times 0.6. So we get 0.32 plus 0.36, which is 0.38. What? 0.68. Okay, the weather is fine on Paradise Island given that the flight departs on time. So the probability of fine given that it departs on time, we know that's fine and on time over the probability that it departs on time, which we just found. Fine and on time we know is 0.4 times 0.8 over 0.068, which is 0.32 on 0.68. Which is 32 on 68. Divide them both by 4, 8 on 17. Okay. So we'll leave it there for the moment, and I'll create a new video for independent events. So hopefully you're starting to get this. I'll go through independent events in the next video. Good luck with that. Bye.